This is Jack Jackson with part 4 of our series of lectures on inferential statistics. This particular one is on an introduction to using the TI-84 to help us with inferential statistics. So there's several shortcuts that are built in on the TI-84, and specifically we're going to focus on one sample Z confidence intervals and one sample Z hypothesis test. So we're going to do both hypothesis testing and confidence intervals with the TI-84, and this gives us a good introduction to this basic concept. The calculator actually has lots of different possibilities and different things that it can do with this area of hypothesis testing and confidence intervals, several different variations on a theme. But this is a good introduction. Once you learn how to use these two, then we'll be able to quickly expand to the others as well. So let's start by pulling up our calculator emulator here. Now, first of all, let me just remind you that we have under distribution, second variables, we have normal PDF, normal CDF, and inverse normal. Remember, we use normal PDF to get the graph of a bell-shaped curve, our normal curve. We use normal CDF to compute probabilities, and inverse normal we use if we know the probabilities and we want to compute the Z values or X values that give us those. And notice there are a lot of other things below that we may come back to later. Now, if you go under statistics, you will see some things that we've already looked at. We have edit, which is how we go to our data editor. We have calculate, and there we calculated our one variable statistics. Also regression that you may have worked with in your algebra classes. And then we also have tests. And tests is where we want to go now. So let's look at that again. Let's clear this out and go over the steps again. So to get to test, what you want to do is hit stat. The quickest way is left arrow to tests, and there we have it. We have a Z test and we have a Z interval. And we also have a T test, a 2-sample T test, a 2-sample Z test, proportion test, and so forth. Right now the ones we're interested in are 1 and 7, but eventually we'll go over how to use all of these different ones. So for example, if we want to, well, I'll tell you what, for examples, let's pull some problems from the homework here. And so if I go to, let's see here, course compass, and if I go to do a homework, oops, okay, and let's go down here and do some Z interval homework. Okay, and I'm going to go in here somewhere and pick a question. I think this may be a good question. Actually, this may not be the best question. Okay, this will work. We have a random sample of 250 students at a university, and we have a mean of 15.5 credit hours taken per quarter, so they are on a quarter system rather than a semester system, and it has a standard deviation of 2.2 credit hours. Estimate the mean credit hours taken by a student each quarter using a 90% confidence interval. So, a couple things we got to make sure before we do this. We're estimating means by finding a confidence interval. Okay, so we're estimating means. Second thing is we're going to assume in this case that the standard deviation is actually known. Okay, now in this case we actually have a very large sample size, 250. It turns out we're going to see later on that if the sample size is not real, if the standard deviation is not known, excuse me, if the population standard deviation is not known, we should really be using a t-test. But it turns out if the sample size is very large, there's so little difference between a t-distribution and a normal distribution that we can get by with using a normal distribution. So in this homework, particularly if it's in the Z interval homework or the Z test homework, assume that you can use a z-interval or z-test, that notice the sample sizes will be large. So many of the textbooks will talk about a large sample methods, and they're wanting you to use a z-test if the sample size is very large. But properly speaking, we should use that when we know sigma. But we're going to assume that this 2.2 is essentially the standard deviation of the population. So this is the setup that we need, and we need the sample size to be at least 30 so that our distribution of sample means is approximately normal, which of course 250 is plenty enough, so we don't have to know anything about the underlying distribution of individuals to work this out. Okay, because of the sample size being large, we can use a z-interval. Okay, now let's look how we can do this on the calculator. Okay, so on the calculator we're wanting to do a z-interval. So after I went stat, left arrow to test, I'm going to choose number 7, a z-interval here. And we can input our stuff from either statistics or data. This is where they've given us the statistics. We enter the population standard deviation, which is 2.2 credit hours. 2.2. Move down. We put in the mean. That's the sample mean, 15.5. That's going to be right in the center of our interval. We put in the sample size, 250. And we need to put in the level of confidence. That's the 1 minus alpha level. So in this case, that's 0.90 or 0.9. And once we've entered all that in, we just simply hit calculate. Isn't that cool? And it returns everything. The only thing it's not really showing on that screen is what the level of confidence was. But of course, we had to enter that in. And there it gives me a confidence interval. Now, this is given a little bit different way over here. Sometimes it's given as the sample mean plus or minus a certain amount, and so we can figure out what that is. If we just take this upper one, for example, 15.729, and we subtract the 15.5, I can do that in my head. That's 229, 0.229. And if we add 0.229 to 15.271, then that will give us the 15.5. So 0.229 is how much you're going up and down. So the 15.5 plus or minus 0.229 is the correct answer there. And I can have it check it. All right. Good job. Always like to see that. Let's do another exercise. Alright, let's try. Let's see here. Let me find one I'd like to try. Let's try this one. See what happens here. Healthcare workers who use latex gloves with glove powder on a daily basis are particularly susceptible to developing a latex allergy. Each in a sample of 49 hospital employees who are diagnosed with a latex allergy based on a skin prick test reported on their exposure to latex gloves. Summary statistics for the number of latex gloves used per week is X bar is 19.7, and we know the population standard deviation is 12.3. Give a point estimate for the average number of gloves, latex gloves used per week by all healthcare workers with a latex allergy. Well, assuming this is a random sample of healthcare workers with the allergy, then the X bar is our best estimate of the population mean. So 19.7 is the best estimate there. That's an unbiased estimator, and it's a minimum variance unbiased estimator. Now, form a 95% confidence interval. So we can use our calculator again for that. So again, let me clear this out so you can follow the key press history there if you want to see the keys off to the side. So we start by hitting stat, left arrow. Now we're wanting to find a confidence interval. We know sigma, the population standard deviation, and we're trying to estimate a confidence interval for the mean. And our sample size should be large enough that we can assume we have some assumption of normality here, and that is if the sample size is 49, well, that's bigger than 30. So regardless of what the underlying distribution is, that's good enough to tell us that this has a normal distribution for the sample mean. So that's all that we need to use number 7. So we have to check those basic assumptions before we can use this. Now, we're doing this from the statistics. This time the sigma is 12.3. Be careful whether they give you sigma or sigma square. In this case, it's the population standard deviation is 12.3. That's sigma. That's what this asks you to input. Then it puts in the sample mean, which is 19.7. Of course, that's going to turn out to be exactly right in the middle of our interval. So it's going to be 19.7 plus something for the upper limit, and 19.7 minus the something for the lower limit. That something that we're adding above and below is our error of measurement, our margin of error, our largest error. Now, the n is the sample size, and that was 49. And what level of confidence do we want here? Did it say? Right here it is, form a 95% confidence interval. So that's going to be 0.95. And we get there and we calculate. Isn't that see how sweet that is? That is so really cool that will work out and just pretty much do all of it for you. So the very, very powerful built-in stuff for the calculator there. Because these z intervals and the z-test and these other hypothesis tests and confidence intervals are so important, they've built in a lot of shortcuts for us. So we have to enter in this information here. Let's do this here. Okay, so we can get both of these on here at the same time. Okay, so this was, let's see how far they want us to write. Decimals, 2 places. Okay, so 16.26, and for the upper, 23.14. Okay, what else do we have? Give a practical interpretation. Okay, so this is a 95% confidence interval. So I'm just going to say it without doing it. On average, if we were to repeat this process over and over again, 95% of the time, a confidence interval generated in this manner will actually contain the actual mean. Let's see what we've got here. One can be 95% confident that the average number of latex gloves used per week by all healthcare workers with a latex allergy is in the interval. That's correct. Let's look at the others and make sure they're not right. 95% confident that is used is lower. No. Greater than the upper? No. It's between the two in the interval. And definitely not D. So A is the correct answer there. Okay, what do we need it to be valid? We kind of went over this already. We do need the sample selected randomly from the target population, and the sample size needs to be large, at least around 30. Okay, so I believe that's A. And that should be good, and I believe everything checked out there. Very good. Okay, so that gives us some examples of how we can form a confidence interval. So the z interval, we did that. Let me look at another example here, if I can find one that I did this with. I think there's an example somewhere. Yeah, here's one. Let's get back to that one, if I can find it again. Here it is. Okay, let's look at this example, and we'll do at least part of this. So here we have a sample size, actually 2 samples, and we're going to make 2 different confidence intervals and compare them. I'm actually not going to do this entire exercise. I'm going to leave it to you to finish it up. But we're going to do part of it just to show you one other feature on the calculator. So what I can do is actually enter this information into our calculator by entering stat and number 1, edit, and let's get in here somewhere and let me clear that list. Actually, I'm going to clear a couple of these lists out because I don't need them, just to clean things up a bit. Okay, but clear out list 1 and type in the data: 70, 45, 54, 68, and of course double check your typing here, because you don't want to miss a whole question just because you type in something incorrectly. And of course there's no getting out of actually typing in the data. Somebody's got to type it in. Now somebody may have typed it in and can send it to you as a list, or they could, once this is saved in some kind of program, there might be a way to electronically get it around, but somebody's got to type it in at least once. Alright. Hopefully you're doing this with me. If not, whenever I finish, go ahead and press pause and get caught up with me. Okay. You want to, anytime I'm doing any of these lectures, you want to be sure and use the calculator to do these things. Now I got 36 different data values, and that looks like that's the correct number. Hopefully I've typed everything in correctly. I should probably go back and double check right now, but I'm going to trust that I got it right. Now we want to do a hypothesis test, or not a hypothesis test, confidence interval for this particular data set. What is this? This is 20-year-olds on some 25-year-olds on some kind of IQ test. Okay, and there are 36 of them, and we want to get a confidence interval for the average. So this is a sample of size 36. Now since the sample is size 36, we're going to, well, really properly we should probably do a t-interval, because we don't really know the population standard deviation. Okay, but let's just figure out what it is, and let me do a couple things here. I can do stat calc, one variable statistics for list 1, and notice it will compute x bar and also will compute 15.3 something for the standard deviation. Let's suppose that we actually know the standard deviation of the population really is, say, 15.3. Let's just say we actually know that. Okay, let's go now and do stat, go to tests, and we're going to do an interval, number 7, a z-interval. Now this time we're going to do it from data. And when you click on data, some of the things change. Now back up, let's look at when it said stats, you have to enter in the value for x bar in the confidence level and the sigma. If you put it on data instead, you have to put in sigma. What did we say it was going to be? And I forgot now what we said we were going to use. We were going to use 15.3. 15.3. Okay. 15.3. Okay. And so for sigma we're going to use 15.3. The list tells us where our data is actually stored. So this is going to actually compute. It does the same thing as before. It computes the mean, x bar, but it does it from the data. And you can also have a frequency table. If all your data is in, say, one list, you just leave the frequency to be 1. But you can also have a frequency table where we have data in, say, list 1 and list 2, the corresponding frequencies. Okay, this one we want a confidence interval of 99%, so C level is 0.99, that's our 1 minus alpha level. And once we've got all that, we can just go here and hit calculate, and it go ahead and figures out the interval for us. It also went ahead and told us what the mean was and what the standard deviation of those particular sample was, and n is 36. So this may or may not work out correctly because they wanted us to use I think the S of x to estimate the sigma. Okay, now that shows how you can use some data to figure out, basically to figure out the x bar, and it kind of does that internally. So notice that what we're doing in all of these cases is it's basically using this formula right here, these formulas, particularly this this one in the middle, to figure out the margin of error, the E, maximum error. We know the sigma of x's. We tell it the sample size n, or we enter a number of data values and it can count how many are in there, so it knows n. And then we give it a, well, what we actually give it is 1 minus alpha, and from that it can figure out 1 minus alpha over 2 and do an inverse norm of that. So that's going to output the x value, actually a z value really, that goes with that. Multiply that by sigma of x's and divide by square root of n, and that will give us the margin of error. Then the interval goes from x bar, which we know, minus e, up to x bar plus e, from x bar minus e to x bar plus e. That's our confidence interval, and that's how we compute it. Now we can also use this bottom formula version of the formula. Really, all three of these are really saying the same thing. They're just kind of solved different ways. The first one is solved for the confidence level, 1 minus alpha. The second one is solved for the standard error or margin of error, E. And then the last one is solved for n, the sample size. So all three of these basically give us the same relationship that's among alpha, n, and E. We can use the last one sometimes too. Let's see if we can find a homework problem based on that one. I think some of these at the end are based on that one. Okay, here's the sample size we're looking for. Suppose you wish to estimate a population mean correct within 0.14 with a confidence level of 0.90. You do not know sigma square, but you know that the observations will range in value between 35 and 43. Okay, now this time you really need to know sigma square to be able to do this. But in this particular one, what they're asking us to do is assume that the range will be equal of observations will be 4 sigma. Okay, so we're going 2 standard deviations above and below the mean for our range. Okay, so with that that in mind, we're going to use that estimate. Okay, so let's see, the range is 43 minus 35. Okay, so 43 minus 35 is the range. Okay, and that's going to be equal to 4 sigma, so we divide that by 4, we're going to get our estimate for sigma. Now that is definitely just an estimate, but that's what they want you to do in this particular problem. So we're just going to assume that we actually know sigma square is actually 2. That's essentially what they're doing here, or at least we're going to use that as an estimate. So if we know that, then we can go on like this, and we can use this formula right here. Okay, so it's this one at the bottom. Let's see if we can work this out here. So we need parentheses. We need let's do the parentheses for the numerator. Inverse normal, remember that second distribution, second varies. Inverse normal is number 3 of 1 minus alpha over 2. Okay, now let's think about this a minute. We want to produce a 0.90 as a confidence interval. Let's work this out first. So 0.9 is the 1 minus alpha. So if we subtract 1 minus that, we're going to get alpha, 0.1. We can do this in our head, really. Divide that by 2, we get alpha over 2. And then what we want is 1 minus the alpha over 2, which is 0.95. Okay, so that's our 1 minus alpha over 2. So that's what goes in this inverse norm. Okay, now let's go ahead and work out this formula. So it's parentheses, parentheses, inverse norm, second varies, number 3, the point, it was 95, close parentheses, times the sigma of the x's, which we assumed was going to be 2, close parentheses, divided by the margin of error, which was, we wanted it within 0.14, so it is 0.14 there, close the numerator, divide by, I'm sorry, I've already done that, that was the denominator, close the denominator. Now what I need to do is square it. Come on, there we go. Check my parentheses. Yes, that's what we want, and this will give us n. Now remember, n's got to be a whole number, and you always got to go up. So if this is 552, we always go up. Even though it's 552.1, we're going to round, not round, but it's a round up, not round off. So we're going to go up to 553. So if our sample size is 553 or higher, then we can work this out just fine. Unfortunately, the calculator does not have a shortcut for that finding n there. What it does have is ways to plug this in. It does have the inverse normal, and the rest of the numbers you just plug in. So that was 553, wasn't it? 553. 553, and we could even check that if we want and go on. Now, they made an assumption there, a conservative, that sigma was 4 sigma was the range. If we go to 6 sigma, that's a less conservative. That's going to actually be a smaller sigma, and will be to get us, if we have a smaller sigma, what does that do to our number here for n? Well, the smaller sigma is the smaller you're going to get for n. Look at the formula here. As the numerator, sigma of x is into the numerator, when that gets smaller, so does n. E is in the bottom, so if e gets bigger, n gets smaller. If e gets smaller, n gets bigger. Okay. Now let's keep going here and take a look at how we can use the calculator to do some hypothesis testing. So let me go back to our homework here for some more examples. In this case, I want to let's see. We want to go back. So let me get out of that altogether and go to some homework. Let's see. Do some more homework. This time we're going to do some on z-testing homework. And again, we're going to see how we can use our calculator to help us. Let's try. Let's see if this is a good one. Okay, this will work. And we don't need a, anytime they give you these tables of areas, we don't need that. We're going to use our calculator for that kind of stuff. 36 tells us that the sample size is large enough that regardless of the underlying distribution, the distribution of sample means is approximately normal. That's important. That's something that we're going to need to make this test work for us. The other thing we need to know sigma, the population standard deviation. That is 8. That we know. The null hypothesis is that the mean of the population is 36. And our alternative hypothesis is that mu is less than 36. So this is a one-tailed, a left-tailed test. Okay? And let's see if we can do this on the calculator. So, we're going to clear that out. Let's just do this. And clear everything out here. Now we're going to go to Stat, Test again. And this is a z-test, so it's number 1. And we're entering the information from the statistics, summary statistics. The mu naught is 36. That's the hypothesized mean. The hypothesized standard deviation is given, the population standard deviation of 8. X bar is something that they had to have measured from a sample, and but that's given to us as 32, and the sample size is 36. Now, our alternative hypothesis is given by this line here. So if it's a not equal to, that's going to be a two-tailed test. If we're trying to say that the mean is less than the mean mu naught, that's a left-tailed test, which is the one we want in this case. If we want a right-tailed test, we go over to the next one. Now you have actually two options here, calculate and draw. Let's do this to calculate first. If I hit calculate, it will calculate, well, everything we need here. We're testing for mu less than 36. The z value that's the z value of our test. That's actually our test statistic is -3. That's kind of our z star value. The p value that goes with that is 0.00134996672. X bar is 32 and n is 36. The last two numbers we typed in ourselves, as well as this up here. So the things it produced for us for an output were a test statistic of -3 and a p-value of 0.001. So the test statistic for z is -3. Okay, and the p-value was, see, round to 4 decimal places, 0.0013. Okay, so we see that this produces both a p-value and a test statistic, so it can be used for either the classical method or the p-value method. Let me also show you something else, though. If we, let's see, clear that out, and suppose we start here, stat, test, again a z-test, let's use that one. Leave everything like it was, and by the way, notice it remembers what you put in last time, so if you want to do this again, you don't have to retype. But let's go to draw this time, and click draw, and notice it constructed a value there, and it draws in the p value of 0.0013, and I believe this is shading, if I remember right, this is shading the p value instead of the alpha. It's hard to see it here because it's so small you really can't see it. Let's do another example. So stat, test, okay, and to make it a much larger, we would need an X bar that's much closer to the mean. So what if we work this out, but this time a different sample, and we only had, let's say we had 35 for the sample mean, okay, and this time leave everything else alone and do a draw. Okay, and we get that. Okay, and so this should be a p-value here, is what you see here. Not the, notice there's no alpha value on this one. It's just a p-value. Okay. So really, this is really set up more to follow the p-value approach because it shades the p-value area, not the critical region. So this is the p-value area of 0.2266, and that's what you want to compare to your alpha. Okay, so in this case, alpha was 1% or 0.01, and of course this one here is much bigger p-value, so we would fail to reject there. And our test statistic of negative 0.75 is this x value that's right on the edge of that region. Okay, on the other hand, let's go back to the one that we actually had in the homework. If we go back to that one, let's see, let's go back here and change this mean to back to what it was in the homework of 32. And again, I can go to draw, even though I'm not going to be able to see it very well. I can do it anyway. And what's shaded is way over here to the left at -3. Somewhere on here is -3, and to the left of that is shaded. So just a little bit there that's shaded. It's an area of 0.0013. That is an area that's smaller than alpha, and so we do reject the null hypothesis. Okay, and so let's see what this says. Reject or not? Well, in this case, the p-value is less than alpha, so that's when we do reject the null hypothesis in favor of the alternative. In other words, there is enough evidence. The data provides enough sufficient evidence to conclude that the mean is less than 36. That was what we tested for. So there is enough evidence to support the alternative hypothesis. Okay, and so there is an example of a z-test. Let's do another one. Let's see what we've got here. Find another good one that I want to try. Those are all basically the same. Okay, so here's a left-tailed test with alpha is 0.1. So how would we do this? Okay, so what we're looking for is basically just going back to our normal distribution. So we can clear a drawing off, and we can go to distributions, and we can go to draw, shade normal, and we want to shade, I believe, I'm trying to remember how the syntax is for this one. I think we can go from, I think this gives it, you give it a left and a right. So we can go from -10 up to no, I need to find inverse norm first, excuse me. So I need to find the critical value first. And so that's going to be an inverse normal. So, try again. Or 3. Inverse normal of 0.1. If it's a left-tailed test, that means you have a 0.1 area to the left, and it's a standard normal, so we can just close it off there. I'm going to store that as C for critical value. Okay, and now what I want to do is I want to maybe shade that and to draw the picture. So now I can go to distribution and go to now go to draw, and I think I can go, shade it. I think this is the syntax. We'll find out. -10 up to C, and you can give it the mean, the standard deviation, but this is a standard normal, so I can just stop there, and I think this will draw it. It'll shade from -10, well, negative infinity really, up to here. Well, the words are cutting off a little bit of my graph there, but you can see the shaded region there, and that area is 0.1, okay, or 10% there, 90% unshaded, 10% shaded, and that is negative 1.2816. 2 decimal places, negative 1.28. Let's see, is there any more to this one? Okay, that's, continue. Okay, which one is the graph? Well, which one did our graph look like? Well, it was a one-tailed test, and we had 10%. That's the rejection region, and do not reject is the unshaded region. Okay. So notice that again, just like in the confidence interval case, if I go to stat, let's say we want to use that same information I have in there, and we go to test and we do a z-test, and I could go from data and let's see, what is the remember what the mean was. The mean of the sample mean is actually 67.7. Let's say 65 is the hypothesized mean. The null hypothesis is 65. Okay, and so we can go to stat, and let's suppose that 15 is the standard deviation of the population. So let's assume that sigma is 15 and that mu sub 0 is 60, let's say 67. Okay. Now let's take a look and go to stat, test, z-test. We can use that data. We put in the mu of 67. That's the null hypothesis mu. The sigma, which is supposedly known if we're using this test. Our data is in list 1, and that'll use list 1 to compute the x bar. And we can do a one-tailed test or two-tailed test. If we do a two-tailed test, for example, here, then when we draw it out, we're going to get that, we get a p-value of very high, 0.8155. Very unlikely then that this is going to be from a different population. So notice though it's centered on both sides, so that 0.8155, half of it is in the right tail and half is in the left tail. Okay, let's do another one. Okay, suppose we do this again and we get a different, suppose the target mean was not 67, but suppose it was 65. Okay, and let's again do a two-tailed test. This is shading the p-value. So p-value is 0.3014. So that's about 30%. Well, it's about 15% in each of these tails. Again, that's a pretty large p-value, so we're not going to reject the null hypothesis. We're going to assume that it's probably true. Okay, but what if we had a different situation here? What if, now I keep changing the target mean, in reality this is not what would change. What would change would be the samples, not the target. So we're going to go here and do a one-tailed test. So this time I'm going to look at a one-tailed test. And let's again draw it out. This time I'm testing that is bigger than, this mean is actually bigger than the target mean, this hypothesized mean. And notice here we get the tail is on the right side, and this time the p-value is 0.0128. Well, it depends on your alpha level whether that's good enough. If your alpha level is 0.01, 1%, this is not good enough to reject the null hypothesis. If you're using an alpha level of 0.05, then, or say 0.1, then it is good enough. So remember, you reject the null hypothesis if p is less than alpha, and you fail to reject if p is greater than alpha. The point I'm trying to show you here is that you can use the calculator here to either go to stats on a z-test and enter in mu naught sigma x bar n, and then whether you want this next to last line gives you the alternative hypothesis basically, and you can either just calculate the numbers or you can draw it out and calculate it basically. Or you can go to data and it will pull your data from some list and use that to calculate the x bar. But again, you still have to put in mu naught. That's the hypothesized mean from the null hypothesis, and sigma is the population standard deviation, which is assumed to be known in the z-test. So there's a good introduction to the calculator, TI-84 calculator, and how you can use it. Very much shortcuts the whole process of finding confidence intervals and hypothesis testing. So it makes it very easy actually to compute both a confidence interval and a hypothesis test. And that was for a z-test and a z-interval. If you also look here, we go to stat and test. There are many options here, and we'll see later on what each of these mean. A t-test, that one's used if you have the same situation we just had, but you don't know what the population standard deviation is. So actually, t-test is much more often used than a z-test because that's a much more realistic situation. Sometimes we have two samples rather than testing a sample against a known mean and standard deviation. We're testing two samples against each other to see if they come from different populations. Okay, and that would be if we know the standard deviation of the outer population, and then if we don't, which is more likely, we're going to be a two-sample t-test. Proportions here are testing for proportions. Essentially, those are from binomial probabilities. And then we have confidence intervals, the z-interval, a t-interval. Those are one samples. And then if you have two samples, these are the intervals for the differences in the samples, differences in the means. And somewhere down here, some of these tests can be used for comparing variances as well. So we'll look at some of those examples at a later time. Hope that's helpful. Bye-bye.